It's a good thing that maybe that the task is to find something to say about each speaker not available through Google rather than, say, Cambridge Analytica. Okay. All right. Okay. I frankly wondered what I would say, and the talk that you are about to hear is based on a kind of minimax approach in which I hope that no one will be utterly bored by absolutely everything I say. Okay, so I want to talk about two problems of fitting manifolds to data. There is an intrinsic flavor and there is an extrinsic flavor, and both of these tie in. Although, all right, so I mean, you can see the evidence is on Google, for example. I am a joint author of the papers that I will be speaking on, but I'm not the main contributor to the papers that I will be speaking on. But these papers relate to something that I have been studying for a very long time. And so that is a third flavor of the problem, which maybe I will discuss a little. All right, so let me start with the extrinsic flavor. So we are in some very high dimensional Euclidean space, Rn. It might be Hilbert space, but let's just keep it Rn. Distances are always just the Euclidean distance, okay, for this problem. Now, we are given a large collection of data points, let's say x1 through xs. S is the sample size, okay? And so these points lie in Rn. They are sampled independently at random from some completely unknown probability distribution, which I will call dp. So this is an unknown probability distribution on Rn. Okay, and so these are sampled independently from that. And based on viewing these, we would like to test the hypotheses. Right? We'd like to test the hypothesis that this probability distribution is concentrated close to a low-dimensional embedded manifold with reasonable geometry. Okay, why do we want to do that? Well, people who study the real world say that this is a useful hypothesis. I certainly don't know anything about the real world, but this seems like an interesting problem. So we want to test the manifold hypothesis. So we want to test the hypothesis that there exists an embedded manifold of some lower dimension, let's say D, sitting inside Rn with reasonable geometry. Such that dp, this probability distribution, is concentrated close to M. Okay. Now, so that's the extrinsic problem. Of course, this problem is not well formulated. What does reasonable geometry mean? What does concentrated close to M mean? And for that matter, what does it mean to test the hypothesis? Okay, well, first of all, let's do the easy thing first. What does it mean to say that P is concentrated close? So let's say I'm going to take the expected value under the probability distribution dP of the squared distance to the manifold. So I take a point x, which is sampled according to dP, and I take the distance squared from x to m, and I would like to say that the expectation of that is less than epsilon. And so let's say I specify epsilon, and that will be, that's what I mean by concentrated close. I would love to be able to deal with a particular epsilon, but there will be some slop. Maybe in the good case, I will be able to achieve 100 epsilon, and in the bad case, I will know that I cannot achieve epsilon over 100 or something like that. Okay? Immediately, this is subject to trouble for the following reason. I want to make no assumptions on dP. The only thing I know about dP is that is that these points are sampled from it. That's all the information I have. Imagine that dp has a tiny, tiny, tiny probability, much smaller than 1 over s, that the point x is out in the Andromeda galaxy someplace. In that case, this expected value will be a small probability multiplied by a huge number, and I will be out of luck and I will fail to see that. So it is impossible to test something like this unless I make some assumptions. And so what I'm going to assume is that this doesn't live on all of Rn, but lives on the unit ball, the ball of radius 1 about 0, about the origin in Rn. So this number 1 is a unit distance. That's as far away as...
Think of n as a capital N, is that fixed and large?
Oh, capital N is arbitrarily large, and it's very important that constants, it's varying. Various things are supposed to be independent of n. The fact that this is 1 instead of some letter of the alphabet is, of course, irrelevant, because I can just scale my data. But it means that various formulas that look dimensionally incorrect are actually perfectly all right, because the unit, that specifies what a length means. OK, so all right. I would also like to say then that this m is contained in the same ball, B01. OK, so all right, I've now fixed the trivial fatal error. And so this, maybe I will put a symbol like that indicating that there's some slop in the epsilon. But the slop is not dependent on capital N. Capital N could be infinity without loss of generality. I could be working in Hilbert space. OK, yes?
So, you said that you didn't want to put any conditions on dp.
Right.
Now you've just given a very strong condition.
That's correct. That's correct.
Are we allowed to think in the background that if you assume some kind of decay rate as you went out, or
yeah,
is that going to lead, or is that lead to a fatal?
No. The one way to think of it is p can be absolutely arbitrary, but if I see any data points from the Andromeda galaxy, I will ignore them as outliers, and they will not count in this.
So you put a condition down, but if I sat down and I said dp is decaying, exponentially.
Right. Oh, as long.
Does that lead to? Am I going to get in trouble somewhere later on in an argument you're going to make, or is it? You can relax that assumption. That's your question. I think you can relax that assumption. Okay. So this is what it means, concentrated close. What does reasonable geometry mean? Well, reasonable geometry, of course, is in the eye of the beholder. Here's what it's going to mean for purposes of the extrinsic problem that I will talk about. So reasonable geometry means two things. First of all right, so M is of dimension d, so it has a d-dimensional volume. And I'm going to specify a bound for it. And again, this bound is subject to slop. Maybe in the good case in which the data really do lie close to something here, this volume will be less than 100 times v. And in the bad case, I will guarantee that it cannot be done with volume less than v over 100, something like that. But the constant 100, which in fact will be a much worse constant than 100, none of this is actually practical. The implied constants here, again, are independent of capital N. Capital N, again, could be infinity. We could be working in Hilbert space. OK. So that's one condition. The other is that the reach of M is greater than or equal to some number tau. Now, the reach of M is a distance, and I don't know how well known this concept is. When I first became involved in the production of this paper, I didn't know what it meant. Let me describe it and tell you what it means morally. All right. So here's a manifold M, and we look at a point, not necessarily on the manifold, but not too far from it. If this point is of distance less than tau from the manifold, then there must be a unique closest point of the manifold to that point. That's what reach means. It's the largest number tau for which that property is true. Okay. What does that mean? Let's give some examples. Well, first there's
there's an infinitesimal condition, a purely local condition for the reach, which is that all the sectional curvatures are less than tau. Think of a little tiny circle, or think of a parabola with enormous curvature at the tip, and if you are right there, you are very close to the manifold, but there is not a unique closest point of the manifold. So having a lower bound for the reach tells you a local condition on the curvatures, but there's also a global aspect to it, because, for example, if you see a spiral locally, did I say the sectional curvatures? I'm sorry, the principal curvatures. This is embedded, I'm sorry. I mean, here, the principal curvatures are very gentle, but this has a lousy reach because this point is equally close to these two. So we're going to assume a lower bound for the reach, and so these are our conditions. Okay? Now, what does it mean? What does it mean to test the manifold? So the manifold hypothesis is going to be that there exists an embedded d-dimensional manifold. D is given. Think of D as being 3 or 5, okay, nice and small, whereas n is enormous. So we're going to test the hypothesis that there is such a manifold having these properties in such a way that this is true. Okay, that's what we're supposed to test. Now, how do we test it? Well, we are supposed to produce an algorithm. And the algorithm takes some inputs and it produces some outcome. The inputs to the algorithm are the parameters epsilon, v, tau. How about d? Let's input d. Okay, the dimension. And one other parameter, delta, which I haven't mentioned yet. Delta is going to be a bound for the probability that the algorithm makes a mistake. Okay, so those are the inputs, and x1 through xs in our Rn, where s is big enough, s is greater than or equal to s min of these parameters, d, epsilon, v, tau, and delta. Okay, where this fellow should be computable, and in fact, the paper gives bounds. I'll come back to that. So those are the inputs. Okay, so the parameters of the problem and enough sample points. What are the outputs? What are the outcomes? There are two possible outcomes depending on the data. One outcome is that the computer says no go, sorry, I'm unable to find a manifold, in which case presumably there is no such manifold. Okay, or let's see, how many? I guess I should come over here. Or, okay, or a manifold M of dimension D with, satisfying those conditions. So volume of M less than or equal to C times V. C depends only on D. Reach of M greater than or equal to tau. Little c times tau. This little c also depends only on D. And let's see what else. Okay. Well, it does that. Now,
what does that mean it does it? How does it give it to us?
What a good question. Okay, so first of all, this manifold sits embedded in a relatively low-dimensional space. Again, I'm not talking about anything practical, but this sits inside a vector space of the enormous Rn of dimension controlled in terms of these parameters. And then once it's in there, then it's given by a finite number of equations which are guaranteed to determine a nice manifold because they're suitably transverse. Okay? Good enough? Okay. So that's what it means that it gives the manifold. Now, all right. So far, I haven't said anything useful because, for example, an example of an algorithm that does this is that the algorithm can always say no go. Thank you. Okay. So we need to do somewhat better than that. And so the property of this, for this algorithm to be acceptable, so let's say the algorithm, so we accept the algorithm. If the following condition is true, pick any dp unknown probability distribution there. Pick any one, okay, concentrated in the ball. Okay, then, all right, also specify the inputs. Then, let's see, okay. Having specified, all right, so specify these parameters and then take these guys by sampling independently at random from dp. Run the algorithm and see what happens. With probability at least 1 minus delta, the following two things happen. Either the algorithm outputs no go, and there is no embedded manifold with parameters like this, where this is a small constant and this is a big constant, these change places. Okay, either there is no manifold with these, with the property that the expected square distance is less than a small constant depending on only on little d times epsilon. That's the no-go case. Or the algorithm outputs this manifold, and this manifold then is guaranteed to have these properties, and furthermore has the property that then this expected square distance is less than big C times epsilon. If all that stuff is true, then we accept the algorithm, and that means that in principle we can solve the problem of testing the manifold hypothesis.
You said big C times epsilon. It's the same big C as there?
Well, I mean, it could be. There's no reason why it should be, but if you want to make it so, these constants have the property that any big C, you know, it's the usual thing. The statement gets weaker as big C gets bigger, and so take all of your big C's and just take their maximum and erase all the big C's and put them all there. And similarly for little C's. If I were trying to tune it, so in other words, yeah, if I were trying to tune it, there's no reason why any of these constants are the same.
Okay. Just to clarify, maybe it's an important point that so S mean is not allowed to depend on capital N, only in the lower dimension.
That's correct. That's correct. All absolutely right.
If you allow it to depend on capital N, that seems still non-trivial.
Okay. Okay. Thank you. Okay. Yeah. Okay. But in fact, it will be independent of capital N.
Manifold can have a bound, doesn't it?
Oh, what a good question. These manifolds do not have bounds, and that this is a compact manifold. Thank you. I should have said, this is going to be a compact manifold. And so one could definitely ask. And in fact, one of the natural questions in this subject is this really what you want? So for example, suppose, let's take a very degenerate case. Capital N is 3. We have imagined that we sample a lot of points which are in R3, which are concentrated very close to a Mobius strip. Well, there is no manifold in R3 that, with good geometry, etc. That suggests that maybe we're not asking the right question. On the other hand, imagine a bunch of points on a sphere in R3 which lie in some Cantor set of on the sphere, on the unit sphere. Well, we don't have complete geometrical information about how these points are distributed, but the fact that they all lie very close to the unit sphere is worth capturing. So okay. Yeah.
Why would a Mobius strip not be nice enough? I mean, locally it's nice,
right?
Locally, it's great. So I would say, yes, I agree with you. What's wrong with the Möbius strip? But the Möbius strip is not a manifold because it has an edge.
Oh, I see, okay.
Okay, so therefore, so Pierre was asking, okay, wait a minute, should we allow a boundary? And well, yes, maybe we should allow a boundary. And then what kind of geometries? All right, I do not.
You also seem to be rolling out hyperplanes too.
Well, so remember, this is all right. All right. Strictly speaking, yes, but morally, no. Okay. So if I mean my probability distribution is concentrated in the unit ball. I said that my manifold is embedded in the unit ball, but I should have said that it's embedded in a ball of radius 10, and there's no difference in the proof. Okay. Fair point. Okay. Yeah. If everything lies on if everything lies on, let's say, a two-dimensional plane, we should allow that as an interesting solution. Okay, I should say, so far I've only talked about the extrinsic flavor. I've given a bunch of definitions and no assertion. But I should say all of this is only the beginning of the subject. These are the easiest questions one could ask, I think. Well, Asaf came up with an easier question: what if the sample size is allowed to depend on n? But I mean, there's a hierarchy of questions of which these are just the easiest and most elementary. Okay, so there is a paper by Sanjoy Mitter. Let me write the names down. Sanjoy Mitter, Harry Narayanan, and me, called Testing the Manifold Hypothesis. Okay, and the content of this paper is that there is an algorithm that does this. Okay, and once you think about it, it's actually not so bad, and maybe I will have time to explain a little. There are explicit estimates for how many operations you have to do. How much computation does the algorithm require? It requires a ridiculous amount of computation. It's very far from practical, very far. There is also an explicit expression that I think I won't write down for S min, which has the feature that it is definitely not optimal, because the other day Aryeh Kontorovich sent me an email saying that he has a better bound, and I haven't had time to check it, but I assume it's fine. So so whatever it says in our paper, disregard it, because it can be very likely improved. Okay, that is the extrinsic version of the problem, and the statement, again, the statement of the result for the extrinsic problem is that there is an algorithm that does this, that is acceptable in the sense that I just described.
Is there something like a null hypothesis, like if there really is a manifold, that you would find it within 95% probability, or something along those lines?
Okay, so let's see. If there is a manifold, right? That's part of being acceptable. If there is a manifold, you will find a manifold that does the job with 95 with probability at least 1 minus delta. Okay. Maybe I stopped writing after I wrote "we accept the algorithm," but yes. So in order to be acceptable, the algorithm has to have two properties. If there is a manifold that does what we want, then with probability at least 1 minus delta, the algorithm will produce such a manifold. Okay. On the other hand, if there is no such manifold, the algorithm will not spuriously produce an M. It will instead say no go.
But the manifold you find may be larger dimension than the actual?
No, the dimension is fixed. The parameters, like let's say let's say the volume might be 1,000 times more than we would like, but only 1,000 times more, some fixed constant. Okay, or the reach, the curvatures, it might be 1,000 times more curved than we would have liked. but within a bound. If you're willing to accept, so to speak, orders of magnitude, then I see puzzlement. So I am not being clear?
Oh, okay.
It's okay? All right. But the dimension's absolutely fixed.
Can
Pierre?
get the manifold given, but the algorithm could be another one.
Oh yes, oh yes, oh yes. So here is a very simple example. Let us imagine that the actual manifold is the sphere, but all the points lie in the southern hemisphere. Okay? Well, then the manifold hypothesis is true, and the algorithm will output something which will probably look a lot like the southern hemisphere, joined together somehow to make a manifold which may or may not look like the northern hemisphere. Thank you, it's an important point. Okay, all right? All right. In particular, that's a significant part of what makes the problem would be a lot easier if we were guaranteed that dp produces points close to any given point of the manifold. So we have to work to guess part of the manifold. Why do we want part of the manifold where there are no points? Well, that's the problem as stated. All right, let's abandon the extrinsic flavor for the moment, and let me talk about the intrinsic version of the problem. Okay.
When you ask the reach to be positive, do you ask the manifold to be smooth, like to ask that at any point you can inscribe a ball?
Yes. Yes. So that's what it somehow that's what it means. Well, inscribe a ball. Wait. I think maybe you and I are thinking too low dimensionally. We're in a big Hilbert space and we have a three-dimensional thing. What does it mean to inscribe a ball? So think that there's I'll be with you in a minute. There's a tubular neighborhood of some around the, let's say, the three-dimensional manifold M. There's a tubular neighborhood of all the points that are of distance less than tau from there, and any point in that tubular neighborhood is closest to to a unique point of M. Okay, so for example, if there were curves in the plane, then you could say that on either side of the curve you can inscribe a circle, and that would mean the same thing. Okay, you had a question.
Oh, I was just wondering, with this algorithm, are we assuming the manifold is connected? I mean, if you have two spheres that live very
Oh,
far apart.
that's a very reasonable question. No, we are not assuming. Thank you. We are not assuming that the manifold is connected.
Oh.
And so, for example, I should have said that back when the paper was a little fresher in my mind. I guess I would have known that, but I forgot. No, the manifold need not be connected. And indeed, suppose that you have two spheres, and
Yeah.
No. It will catch that.
Thank you.
Thank you. Pardon?
But you ask it to be closed.
But I asked it to be closed. So, for example, two spheres, no, compact, no boundary, a perfectly nice manifold, not connected. Okay. Any other additions, corrections? Okay. Let's do the intrinsic flavor. Sorry. Okay. Okay, so in the intrinsic flavor, we don't have data points in Rn. Our data points live in the metric space itself. The only data we are given will be distances, and we would like to think that this metric space we have found lies inside a manifold. Now, this gives rise then to a deep question about which I know basically nothing, and the intrinsic results that I tell you about will be just the baby case of the real problem. So the real problem, which is I think very tough, is given a finite metric space, can you embed it isometrically into a reasonable, or with small distortion, into a Riemannian manifold with reasonable geometry, where you get to specify what reasonable geometry means. Okay. In the baby case, this finite metric space, let's say the metric space is finite, and let's say that what we want about this finite metric space is not that it merely embeds, but that it is isometric, or maybe isometric with small errors. I'll be more precise in a minute. Isometric to a fine net inside a manifold. So a finite set of points of which we have picked enough that every point of the manifold lies very close to one of them. For such a thing, sort of, if you look at the finite metric space and squint, you will see the manifold. Okay. So this is a much easier problem. For the general problem, if you look at a finite metric space and squint, you cannot tell what it may embed into. All right. So, all right. So the paper that I'm describing now is called Reconstruction and Interpolation of Manifolds 1, the Geometric Whitney Problem. Clearly a paper written by committee. So I'll give you the committee in a moment. Okay, so who are the authors? There is Sergei Ivanov, Slava Kurilev, Harry Narayanan. Let me see if there are enough again. Oh. Mati Lassus, dear, I'm so sorry. Lassus, Harry. And me. Okay, a question? On the list of authors?
Squint,
Yes.
then I will not see if it is locally Euclidean, and I will not see if the distance between two faraway bounds is essentially the length of a geodesy.
Yes. Yes. So I'm sorry. So you're saying, isn't this problem easy because? Is that what you were saying?
But I cannot interpret it just by squinting. Yes.
Oh, well. All right. Let me state the theorem, and then we will see. First of all, is it indeed very easy? Well, yes. Actually, I would claim it is. Although details are, as in anything, you have to work out the details. They're not entirely a walkover. But is it fairly described by what I said about squinting? Well, you decide. All right. So in the paper, the paper actually talks about a general metric space and about complete manifolds. I'm going to talk about finite metric spaces and compact manifolds in this talk. So suppose we have two metric spaces, x dx and y dy. I'm going to say they're approximately isometric with parameters eta and delta if the following occurs. Okay, so let's say there's a map F from x to y with the property that if you look at any 2 points, x1 and x2 in X, then if you look at their distances, well, the distances between their images is distorted only a little bit from their, this is the distance in Y, of course. And I'll put here, let's say, 1 plus eta times the distance in X between x1 and x2, but I'll add an error delta so that at very small scales I don't claim that they're approximately the same. And similarly, let's say I have here 1 minus eta times the distance in x1, x2, minus delta. And so this or something trivially modified from this is a very common thing which is used, for example, in geometric group theory, although there typically some of the constants are large, and here the constants are supposed to be small. Okay? So we want that, and we want also another map G taking y to x with similar properties. And these are not necessarily inverses to each other. Okay? So two metric spaces are approximately isometric. So for example, if we have a very, very fine net in a manifold, and if we take one of these metric spaces to be the fine net and the other space and the other to be the manifold itself, they are approximately isometric. Okay? So this delta is a length scale. Below that length scale, all bets are off. And above that, much above that length scale, distances are distorted only by eta%. Okay, so the problem is to decide, given a metric space, in particular a finite metric space, decide, and in particular decide by an algorithm, whether there exists a manifold, and if there is a manifold, then explain it, then produce it, with the property that the given metric space is approximately isometric with given parameters, and the manifold has reasonable geometry. Okay. Now, what does reasonable geometry mean? Okay, reasonable geometry means two things. First of all, bounds on the absolute value of sectional curvatures. And a lower bound for the injectivity radius.
The sectional curvature bounds are from above and below? Or just
Yes,
above?
from above and below.
So it cannot be 0?
No. The bounds, it can be 0. It cannot be plus a billion and it cannot be minus a billion, but it can be 0. Okay? Okay, so the upper bounds on the absolute value. Yeah. Okay? All right, now what? All right, so let's just think about nice manifolds. Again, I'm thinking of compact, but one couldn't, I mean, the paper does complete. So what are the properties of a manifold with these properties? I'm sorry, that's, wow. Donald Trump has the best words, but I seem not to have the best words. Okay, given this kind of equivalence, what can you say about a manifold with reasonable geometry that survives this kind of equivalence? That's there. Those are somewhat better words. Okay. Well, okay. One thing we can say is that at some length scale or other, every ball looks like a ball in Rn. Oh, I forgot to say what the dimension of the manifold is. Oh well, the manifold is of dimension n. It's given and it's supposed to be not very big. Okay, so all right, there is some length scale r such that any ball of radius r looks very close in this sense to a ball of radius r in Euclidean space. That is something easy to decide by an algorithm. Okay? Maybe I will take 2 minutes and explain that, but not immediately. Okay? So that is the first obvious condition. The second obvious condition is what Pierre said, which is that if you have two faraway points and you want to connect them, they must be connected by something like a geodesic. What is a geodesic? What survives about geodesics if you view them this way? And the answer is the following. Here, I should have erased this. This is an extrinsic statement. Okay, so maybe I should say, all right, so first, the ball in the metric space X here, this looks like the ball in Rn of 0R up to some equivalence eta delta. Okay, and the other thing, the property of geodesics is the following. Okay, let x prime and x double prime be any 2 points of X. Then there exists a finite sequence. Let's say x prime is the first of these points. Then there's x2. Then there's xn, let's say, and that's the last one, such that the following occurs. Let's see. The distance between each of these xi and the next is less than delta. So these are all small, these are small jumps. We can get there by small jumps. And the second thing is that if I is less than j is less than k, then the distance between xi and xk, that's obviously less than the distance between xi and xj added to the distance from xj to xk. Thank you, that's the triangle inequality. But the absolute value of this distance, of this difference, should be less than delta for all ijk. Okay? And if things look, if things look like, let's see, I'm trying to think whether I've got this right. It's been a while. I sincerely hope I have this right. Oh well. Yeah, I will look it up in a minute and check. But the claim is that if with suitable eta and delta, if things look like a manifold, then this condition is true. Okay, and the theorem is for suitable ranges of delta and eta and r, that in fact, if these conditions are true, then there is a manifold with bounds on its sectional curvature and injectivity radius in such a way that this can be done. But before I'm sorry, this is much too sloppy, and I will take a look and write down actually what the bounds are. But before I do, let me just take a step back and ask, why should one care about the intrinsic version of the problem? The extrinsic version of the problem is some abstract take on something which is actually used by statisticians in the real world in order to understand data. Where does this problem come from? It's not just fooling around for its own sake. It actually comes from medical imaging. Imagine that you apply some technology to look inside your body, and you look at some goo, and this goo is perhaps not isotropic, but it is the non-isotropy, the whatever, the conductivity or the whatever of the goo inside of you is represented by a Riemannian metric. Okay, I'm not making in the immortal words of Anna Russell, I'm not making this up, you know. Do people know that Anna Russell routine? Anna Russell is describing the story of the Ring of the Nibelungen. It begins in the Rhine River.
She's a musical humorist.
She is a musical humorist, okay? So our story begins in the Rhine River, in it. Okay, if it were New York, it would be the Hudson. Okay, it is a hilarious monologue. I'm sure it's available on YouTube. And at some point, Siegfried meets, whom does he meet? Either Brunhilde or Gutrune, I don't remember. And Anna Russell announces, This is the first woman Siegfried who has ever met who is not his aunt. I'm not making this up, you know. So when I speak of goo inside us represented by a Riemannian metric, that's serious. Okay, I'm not making this up. At worst, someone else made it up. Okay, in any event, that's where the problem comes from. All right, now maybe I will look at my notes and produce a precise theorem and a precise algorithm. Okay. All right, so suppose we have a metric space XD. Let's say it's finite. It doesn't have to be, but I'm going to make it finite. Suppose that it is delta close to Rn. That's this condition. Where'd it go? That's this condition. At scale r. In other words, any ball of radius r looks like, looks like ball in Rn up to error delta in the metric. There's not even an eta, just there. That, and we assume that x is delta intrinsic, which means this condition. This is called delta intrinsic. Okay, and if that is true, then there exists a manifold MG of dimension n such that our metric space is, and now here are the, all right, delta is the length scale, I mean delta is the, yes, and there is a constant depending only on n times delta over r. These are the parameters. Almost isometric to MD to MG. And furthermore, the sectional curvatures are less than or equal to, what is it? Less than or equal to a constant delta over r cubed, and injectivity radius greater than r over 2. That's the theorem, and those conditions are sharp. Now, what do all these conditions mean? Let's take a simple example. Let's say that we have a fine net in the unit sphere in R3. Okay. Okay, so its sectional curvatures are of the order of magnitude of 1. You might wonder, suppose I want to find something for which delta is very small. Well, if delta is very small, then a ball in the unit sphere, so a little spherical cap of radius r, of spherical radius r, looks delta close to a Euclidean ball if it turns out if r is of the order of magnitude of delta to the 1/3. Work it out. Okay, it's a little calculus problem. And so I should think that r is like delta to the 1/3, in which case, let's see. Okay. So we get then a reasonable, I mean, this this delta over R is then delta to the 2/3. If delta is small, that's small. So we're getting, these parameters are small, and so we're getting something that looks usefully like the sphere. What do these theorems say? Here, delta over R cubed is on the order of magnitude of 1, and so we're saying that our manifold has bounded sectional curvatures. That's what we want. That's what the sphere does. And the injectivity radius is at least R over 2. Oops, R is of the order of delta to the 1/3. That's going to 0. So the weak point in the theorem is, wait a minute, we got lousy lower bounds for the injectivity radius. What to do about that? Well, we have the following theorem. If there is a manifold for which the injectivity radius is not so small, our algorithm will find it. And in fact, our algorithm, the manifold that we produce will be, in this sense, almost isometric to that manifold. Okay, so if there is a solution with reasonable injectivity radius, we will find it. But we don't know how to decide just by looking at the metric space whether there is a manifold with a reasonable injectivity radius. Okay, well, so that is the statement of the intrinsic version of the theorem. So we've now covered, I guess this is the usual situation for speakers. I've now covered what I thought would be the introduction to the talk. So I have, let's see, how much time do I have left? Maybe 0, maybe 5 minutes. What do you think?
There's until 2:30, but there's a 30-minute break.
Right. All right, let me not intrude on the break. I will say a little bit about the proofs for 5 minutes, and I will quit at 1:30 faithfully. Okay. All right. Let's look at the intrinsic version of the problem. So for the let's look at the extrinsic. I think given that I have 5 minutes, I should pick one or the other, and I will pick the extrinsic version of the problem. Okay. So let's. All right. If the reach is of the order of tau, let's take a small constant. A small constant, maybe depending on d, times the reach, and let's call that delta 0, and we're going to look on the length scale of delta 0. Okay, let's say that tau is 1. Okay, so this is a small constant. All right, so I'm going to call this delta 0. Now, the manifold has reach at least 1, so its curvatures are controlled. And so if this straight line somehow represents the tangent space, then the manifold does something like that. This distance is of the order of del 0, but this distance is of the order of del 0 squared. Okay, so let's take a projection pi, an orthogonal projection onto this space, which we hope is the tangent space to the manifold at this point, and let's look at the distance, the Euclidean distance between x and pi x, and let's square it. That's more or less the distance squared to the manifold. Well, maybe not. If you're right on the manifold, then that's not a very good approximation. So let's put here delta 0 to the 4th, delta 0 squared quantity squared. This is a pretty reliable estimation of the distance from x to the manifold squared plus delta 0 to the 4th. They're comparable. They most a factor of 10. Okay. Now imagine we cover our manifold by not so many patches. We have a compact manifold. We've assumed that its volume is not so big. Okay, we cover it by not so many patches, and we put these functions together by a partition of unity. Okay, then in a tubular neighborhood of where the manifold is, we don't know where the manifold is. We don't know whether there's a manifold, but we've got ourselves a tubular neighborhood. Perhaps some of these balls are neighborhoods of the manifold, and we don't actually see any points sampled from there because maybe our manifold is the sphere and all the points come from the lower hemisphere. So we may have to guess where these balls are, and we exhaust over a large set of guesses, which is why our algorithm is so absurdly complicated and computationally intensive. But if we have guessed right, then we have made ourselves a tubular neighborhood of the manifold and a function which looks an awful lot like the distance squared to the manifold. Well, not quite the distance squared to the manifold, the distance squared to the manifold plus some small constant. So the Hessian of that locally has lots of big eigenvalues of the order of magnitude of 1 and a few, namely n, the dimension of the manifold, little eigenvalues close to 0. It is then easy to look at something analogous to the critical points. In the 2 minutes, I don't have time to write down a precise definition, but there's a natural notion of a trough for such a function. You can make yourself an n-dimensional manifold. It is not close enough, okay? So the picture that arises is that. The picture that arises is that here is the true manifold, and here's the manifold you construct. Okay, and they are sort of close, but not close enough. However, the manifold you construct has a normal bundle, and these manifolds are close enough that the manifold you want is a section of the normal bundle over the over this guy, which we call the putative manifold, and a section of modest norm. So the problem is, given the putative manifold and its normal bundle, and given a whole lot of data, how do we use the data to construct the actual manifold that we want? Well, because we've got a bundle over a known manifold, we can reduce this to a local problem. So the local problem is that we have some vector-valued function on a ball in Rn, and we want to fit that to data. And Charlie has been thinking about such questions for the last 15 years or so, and so that's actually an easy case of the problems I've been thinking about for 15 years or so. So do that, and then that locally reconstructs this manifold as a section over this bundle. You put those together with a partition of unity, and you're done. And I'm done with 1 minute to go. Thank you.